In this tutorial, we're going to use molecular dynamics for time averaging, a statistical mechanical approach to averaging quantities at the microscopic level to give us a macroscopic value for that quantity. In this case, we're going to look at liquid water, and we're going to average the bond angle to see if we can see a difference between the liquid value and the gas phase value. So the first thing we want to do is create a box of water molecules. We're going to create a relatively small box here for illustrative purposes, 10 by 10 by 10. Here's our water box, and then we choose a methodology. We're going to use amber. We want to make sure we have a constant dielectric because we have real water. We don't want to fake the water. So we use amber, and we're going to use amber 99 parameter set. Before we run MD, what we're going to do is do some optimization of this. We don't want to run molecular dynamics when there are some very bad forces in the system or something. We want to minimize this. We don't need to get it down to absolute zero gradient, but we just want to get rid of all the bad contacts and the bad forces before we run molecular dynamics. So we're minimizing this. All the operations in HyperCam run a lot slower because we're capturing all these images to record them for these tutorials. So things run generally slow when we're recording compared to when one's not recording. Anyway, we have it plenty well optimized. The other thing we need to do before we start averaging, we really need to equilibrate the system. The molecular dynamics we're going to run, we're going to try to get 300 degrees Kelvin. We're going to not have a constant temperature but a constant energy simulation, a microcanonical ensemble. And to get to 300 degrees, we have to really equilibrate for a while. We can do this automatically or we can do it manually. That means that we run for a while. In this case, the temperature is considerably lower than 300. And because some of that kinetic energy was transformed into potential energy, apparently. Anyway, we cancel it and re-equilibrate. What we will be doing is manually getting this towards 300 degrees Kelvin. It should fluctuate around 300 degrees Kelvin rather than drift away or towards 300 degrees Kelvin if it's equilibrated. We could do this much more formally by plotting the temperature or the kinetic energy or by using the heating function that's in there in HyperCam, but we're going to do this manually. So let's do this a few more times to re-equilibrate to 300 degrees Kelvin. When we do this, stop it and start it again, we choose a random distribution of velocities that represent 300 degrees Kelvin, and as long as there's an equilibration between kinetic energy and potential energy, will fluctuate about 300 degrees Kelvin. So we're getting there. We'll do this one more time perhaps. The temperature is now somewhere in the vicinity of 300. It's obviously fluctuating about it, and we can't tell easily whether there's any drift or not at this moment. But for illustrative purposes, this is fine. So let's now assume we're equilibrated. What we want to do now is average some quantity. In this case, we're going to take a bond angle. Let's just choose one water molecule. Choose this one. Name that selection to be, let's just call it angle. So that's angle, and now when we go to molecular dynamics and tell it to do averaging, we want to average the angle and plot the angle as well. So we're ready to go now. We have 300 degrees Kelvin. We're going to go for a picosecond, and so let's just start this simulation. This is the plot of the angle. It seems to be starting out somewhere between 95 and 109 as we go along here. As I said, the capture slows down the simulation, slows down everything very, very much. So what I'm going to do is pause the recording for a couple of minutes here to complete this 1 picosecond of simulation. It'll run much faster if I pause. Well, we're back again recording. This simulation ran for a minute or so while I was not recording, and this is the final result here. These are the averaging of the angle. The simulation is finished, and now what we can do is we can go back into here and ask what is the averaging. So the value of the angle was 101.3 during that period of time. So the angle is smaller than the 104.5 of the gas phase. That this simulation, whether it's accurate or not, we haven't done it terribly accurately, but it suggests that the angle in liquid water is smaller than it is in the gas phase. So that's a time averaging procedure using HyperChem.